Welcome to the session 6 of Unit 1 on digital signal processing. In this session, we will try to understand representation of signals as vectors, orthogonality, and concept of basis function. Actually, there is a perfect analogy between signals and vectors. As the analogy is so strong, the word analogy understates the reality. Signals are not just like vectors, but signals are vectors. A vector is specified by its magnitude and direction. For example, let us consider x is a vector with its magnitude mod x. Let us consider the two vectors g and x as shown. So this is my vector g, this is my vector x. Let the component of g along the vector x be cx. Vector g can be expressed in terms of vector x as g equal to cx plus e. Also, we will consider two more possibilities out of infinite other possibilities. So this is the first possibility where c1x is less than cx, and this is the second possibility where c2x is greater than cx. So there are infinite number of possibilities. Out of those infinite number of possibilities, we have considered only the two possibilities here. Now we can write as g is equal to c1x plus e1, or g is equal to c2x plus e2. In each of the three representations, g is represented in terms of x with another vector called as error vector. So in this case, it could be e, in the second case, it could be e1, in third case, it could be et, so e2. So in each of these three representations, g is represented in terms of x with another vector called as error vector. We have brought these figures from the previous slide for the reference. The error in the approximation is the vector e, which can be given as e equal to g minus cx. E is equal to g minus cx for case 1. Similarly, errors are e1 and e2 for the case 2 and 3 respectively. Now we will choose c so as to get the minimum error e. For convenience, we will define the dot product of two vectors g and x as g dot x is equal to mod g mod x cos of theta, where theta is the angle between g and x. Now, the length of g along x, is mod g cosine theta, but it is also equal to cx. So we can write c mod x is equal to mod g cosine of theta. We will multiply both sides with mod x, so I can write further as c mod x square is equal to mod g mod x cosine of theta, and mod g mod x cosine of theta is equal to g dot x. So further I can write as c equal to g dot x, and this mod of x square I can bring it to the right hand side and I can write it as x dot x. So this x dot x is nothing but 1 upon mod of x square. So ultimately c is equal to what? 1 upon mod x square into g dot x. It can be observed that when a g and x are perpendicular, g has 0 component along x, that is, c would be equal to 0. From the above expression, we are defining g and x are orthogonal if the dot product of two vectors is 0. Now let us go for the orthogonality. The two signals are said to be orthogonal over the time interval capital T if integration 0 to capital T x of t, y asterisk of t dt is going to be equal to 0. So we are taking the integration over the one complete cycle, that is capital T, and we are considering one signal as it is and another in its complex conjugation form, that is x of t as it is, y of t in its complex conjugation form, or x of t in complex conjugation form and y of t as it is. So if any two signals are satisfying this condition, we can say that those two signals are orthogonal. Orthogonality is the property that allows transmission of more than one signal over common channel with successful detection. So the orthogonal signal pairs are, those signals could be two cosine signals with different frequencies, that is m omega and n omega, or those signals could be two sinusoidal signals with different frequencies, or those two signals could be one sine and another cosine signal with different frequencies. Fourth one, those two signals could be TC along with cosine signal, or those two signals would be TC along with sine signals. Okay, so these are the orthogonal signal pairs. Thus, the set of sinusoids and complex exponentials forms two set of orthogonal functions called as basis function. So this is for this today's session. In the next session, we will try to understand eigenvalue and eigenvector with the help of numerical. Till then, keep learning. Thank you.